right, ladies and gentlemen, thanks for coming to my talk in this early morning. So I named it as my talk as a black magic, and I know it sounds cheesy, but I just wanted to attract more people. So basically, I'm going to talking about lessons learned that while I was applying some of the machine learning algorithms from my current company, Mattermark. So I'll start the talk by this metaphor here. So I think the machine learning is a hammer. It actually is a magic hammer. It is a great tool for some purposes. So in case of the magic hammer, it will be good for nail to the wall or for hitting someone maybe. One proverb that I want to mention here is that if all you have is a hammer, everything looks like a nail. What does that have any relation to what I just talked about? So once you know machine learning, you will have an intention to apply this to any problem that you may have in the world. Well, it's not actually going to work that way, because let's say if you are trying to solve the problem of building the house, let's say we are building this place galvanized, then you need a lot more things than just to put the nail onto the wall. You need wood, you need cement, you need the shovel, you need all these different tools combined together with the hammer. However, this machine learning is a really, really powerful hammer. It's really good at doing what it's supposed to do. So that's why I call it a magic hammer. So it's not like the regular hammer. Once you know right way to use it, once you know how you can apply it to your problems, once you know find the where to put the nails on your home building system, it will work out very well. So I will introduce myself. So I'm Evion Kim. I'm lead machine learning engineer at Mattermark. Prior to Mattermark, I was senior software engineer / data scientist at LinkedIn. I've been working on the recommendation systems there. Prior to that, I did my study at Stanford and KAIST. So today's talk is going to be in these steps. So firstly, I'll talk about, so I declare that machine learning is a tool, machine learning is a hammer. So I'll be a little bit more detailed explain about what that means. And after that, I'll do some quick advertisement of our company, Mattermark. And after that, I will talk about one of the most biggest problem that we were facing to solve at Mattermark, namely the funding extraction problem. And I will let you guys know what kind of magic spells that we were able to learn while working on that problem. So this talk is not about learning deep academic technical knowledge about the machine learning algorithms, although I mentioned some names of the techniques. This talk is not about the data infrastructure, although I named some infrastructures. This talk is mainly about tips and tricks on solving the problem that can be done with machine learning. All right, so the first part of my talk, machine learning, the powerful hammer. So I just searched for the Google with the query number trick game. So I got this cheesy only for geniuses quiz. Anyone can guess what the answer would be like? Anyone? So there is actually a debate going on between if it's 90 or 72. I'm on the 90. I think it's 90. I just think it's the given x, return x times x plus 1. There's a So I came up with this example because I wanted to give you guys the idea of what's the difference between the traditional computer algorithms versus the machine learning based algorithm. So I'm going to assume that the answer for that is 90 from now on. So traditional way is that, okay, I want to build a system that's returns x times x plus 1 given the x. So that's actually the only code in my whole slide. So defining the function that's returning x times x plus 1, which is Python code, give it to the computer, and computer is going to translate into the machine the zeros and ones, and then it will know that, okay, I can use the y equals x times x plus 1 as a solution for the given data from now on. So the difference between this and the machine learning way is this. So what machine learning is doing is, instead of just we tell the machine what you need to do to solve the problem, it's rather giving you the data and the model so that machine can be trained by itself. So in this case, we are giving it the data of if input is 2, output is 6, if input is 3, output is 12, blah, blah, blah. And we can give it the model. So this model can be like, there are like numbers of different models. Logistic regression, support vector machine, the deep learning, neural network, all this thing can be the model. So what model basically say is that given this data, try to apply this model to come up with the actual algorithm you will be applying later on when the future data is given. So in this case, for example, we can give the model like, let's think about it as a polynomial model. So whatever the number you got, the polynomial combination of those models will give you the output of 6 or 12 or 20. So if we say that machine learning will go through the data and finding the model that will fit to that data best, in this case, which will be the y equals x times x plus 1. So in the end, it have the same answer for the solutions to come. In traditional way, it got the idea of y equals x times x plus 1. The machine learning way, it also got the idea of y equals x plus x times x plus 1. But the way how it's being done is different. So it's kind of similar in a way that how babies are learning the language, like not in the school, but when they are learning the language for the first time in their life. So my mother is taking a look at this red thing and say the word apple, like multiple times. So that's the data for the baby. So whenever I see that red thing, that's the input, the output is the word apple. So after that happened like repeatedly multiple times, baby is trained in a way that he or she can say the word apple when he or she sees the apple. So how does it, so like I heard some questions from the folks asking that, so I heard the term machine learning, I heard the term deep learning, what's the difference, how they are related? So I have one slide for that. So deep learning is actually the subset of the machine learning. So we can compare it to this slide here. So in here, the left is data, right is the output, then the bottom part is model. In deep learning, you are using the model called like neural networks. The neural network is the model that's trying to mimic the way how human brain works. Not exactly how the way human brain works, because we don't know how the human brain works yet. But we got some concepts of neurons and networks from there and tried to apply it as a model. And actually, recently, it worked surprisingly well on a lot of different problems. So from there, like deep learning became really hot. So the reason why I talked about all this concept of the machine learning is to tell this. So it is not Skynet, at least not yet. It is just like really, really powerful, cool tool for coming up with the mathematical function that can be applied to the problems you have later. I just say not yet because like maybe if we keep doing this, maybe if we keep building this like the mathematical models on top of one of each other, maybe at some point it will start thinking itself, start coming up with its own free will and trying to take over the world. I have no idea, but at least from my knowledge, at least from my colleagues' knowledge, it's not there yet. So it is not Skynet, then what it is? Again, it is a tool. It is a tool for you to use it to build something, to nail down something that can be used for some specific type of problems. So that's my conceptual understanding of myself about the machine learning. So just a quick advertisement from here. So what is Mattermark? So I'm going to talk about this not just for the advertisement, but I will introduce Mattermark so that we can explain more about like what kind of machine learning problems we have at Mattermark and how we use the machine learning to solve that. So what we do, the Mattermark is the, in very simple sentence, Mattermark is the startup database. It's the database that collect and organize the world's business information, especially the business information about the fast-growing startups. So we are collecting this lot of information from the web, public web around the world, and we are applying our techniques to there to make it as a structured database, and we store it into our database, and we are serving it to the users, paid users, with a lot of different mediums like web app, the Excel plugin, Google plugin, Salesforce integration, API, you can name it. So whenever I say about the Mattermark, I get the question of how it's different from Crunchbase. So this is the page that you will see when you are logging into Mattermark. Actually, let me access the Mattermark on live now because we have Wi-Fi. So this is the mattermark.com. If you sign in, it will ask for the password. So this is the page. Once you go into the all companies page, it will show the giant big CSV of the list of the companies. So on top here, it says it has 1.3 million entries, and out of them, we are currently showing the 50. What we can do is we have all the structured data about it. So for example, we can do something like, okay, since we are talking about machine learning, let's find some companies that's related to machine learning. So it shows something like this. Let's say we are filtering it by the companies in the Bay Area. Oh, yeah, sorry. By the way, someone who just talked to me is my colleague, Samir Rahman. He's going to actually talk about this search functionality on 4 p.m. today. So, and I want to do something like I will just be interested in any company that's not too big in a way that it has Series B or Series A or, and also, so by doing this, you can see all this kind of companies that's filtered down. So from the 1.5 million companies, it has been filtered down into the 1,300 companies. We can even do something like, let's filter them by employee count. And list, I want some people, companies that has 50 or more employees. So yeah, I didn't meant it, but the Mattermark is in the third place. So anyway, so let's try click in there to see what kind of information we have in there. So it has information such as what's the description of the company, what kind of tag is related to it, who are the key people, what are the facts, what are the similar companies to Mattermark, and what kind of fundings we received today, up until today, and the trajectory of the companies as well. So that's quick, short advertisement of my company, Mattermark. So as I mentioned, we are using a lot of different machine learning algorithms on solving this problem of building the Mattermark. And mainly, we are using it in places where we want to collect the data, unstructured data, natural language data, and then transform it into the structured data. So one of the big challenges we had to facing was get the unstructured data about the funding event, the startup funding event, and then convert it into this format. How much money, which company, who are the investors, what was the date, what was the series of it. So I'm going to, for the next part of the talk, I'm going to talk about how we solve the problem using machine learning. So prior to actually jumping into the question, so let me talk about one thing really quick. So I used to work at bigger company. Now I'm working at smaller company. So there was a lot of difference that I was able to see between the bigger companies and smaller companies, especially in terms of the machine learning team. So I just wanted to quickly mention that prior to jumping into the actual case study. So good thing or bad thing about the bigger company is that they have a lot of data already. That's the way how they become big. One thing that was very interesting for me to compare was that when I was building the recommendation product at LinkedIn, like for example, I built the people you may know. So let's say you go to your phone now, turn on the LinkedIn and going into the people you may know, and out of 10 recommendations, 7 of them are the one you actually know. What's going to happen is you will freak out and you will think like, wow, how did they do that? It's really freaky, it's awesome. But 10 out of 7 basically means that precision of 70%. So when we were building the recommendation product, precision was important, but it was not that important. So I just stick to the number 70% because that sounds like freaky enough. So we had millions of user interaction data, training data, but our goal precision was 70%. So I joined this smaller, newer, shinier company, Mattermark, and I joined the team. First thing I realized is that we don't have that much training data. Firstly, we are a B2B company, so instead of using the user interaction data, we had to use the manually crafted data analytics team data to train the model, which is in terms of hundreds or thousands if I'm lucky. So let's say you're turning on the Mattermark app and going into the funding history and take a look at the 10 funding history event, and let's say that 7 out of those 10 were correct and 3 were wrong. What did you say? You say it's really, really, really bad because you are the paying customer and we are giving you the right, we're selling the product by saying that we're giving you the right information. So what ended up happening was that I now have much less number of training data, from millions to thousands, but my precision requirement has been gone up from 70s to 95%. So at first that sounds like a nonsense to me. How can I even do that? Am I in the wrong company? So throughout the leftover part of the talk, I will come up with this cheesy slide, namely the spell. So these are the magic spells that I learned, and we will have a total of 5 spells. So after the first spell that I learned from this bigger company, smaller company, the comparison was this one: know your enemy. So at first it didn't seem like making sense to coming up with the higher precision from the lower number of training data. But later I was able to realize that there are a bunch of trade-offs that I can make. So when I say know your enemy, what I meant was that there are a lot of trade-offs: scalability versus accuracy, precision versus recall, engineering versus machine learning. There are trade-offs you can make in terms of where you are putting your resources on. So you need to know what's the bottleneck for that specific problem so that you can ease out the other one. Yep.
Can you give an example of precision or recall?
Yeah, I'll get into that after I talk about this. So the question was, he was asking, what's the example of the trade-off between precision and recall? So firstly, the bottleneck here, the trade-off here was that the millions of training data points sounds awesome, but that also means that you need to build a scalable system that can solve the millions of users. So using the very complicated model on that pseudo real-time system, big giant system, you need a lot of engineering there. However, for smaller company, since we only have we don't have that scalable data yet. We are serving to the only much less than million users. We can use the much more complicated data, complicated model to build a model that's getting us to the higher accuracy. So I'll talk about it a little bit later, but instead of using very simple model like logistic regression, we were able to using deep learning-based feature extraction model, making the vectors dimension much larger than what it's supposed to be, and we were able to do a lot of semantic row labeling. We were able to put all these different, much complicated techniques in there because we had smaller data and smaller scalability issue. So in here, that was the example of the first one, the scalability or accuracy. So if you want to achieve higher accuracy, you can put more resources in there and ease out the resources you will put in the scalability. So the precision or recall, that's the question. So basically the precision and recall, what that means is that like out of the output data, how many of them are correct, that's the precision. And out of all the data available in the world, for example, in the funding case, let's say there are like 10,000 fundings around in the world, how many of them you were able to catch? So that's the recall problem. So every classification problem, you can make the trade-off between precision and recall. If you want to make it like more and more precise, you can make the threshold higher in a way that you will only get out of 10,000, you will get only like half of that, but half of them has like 90% precision. Or vice versa, if you say out of 10,000, like you just like say, everything I received is the right information, then you will achieve higher recall, but you will receive like lower precision. So that's so when we are building the classifier, we can also do the trade-off between precision and recall in a way that how much coverage you want to have versus how much accuracy you want to have. That's the matter of precision and recall here. So get back to the funding thing. Based on Mattermark's data, on year 2015, there were about total of $156 billion of VC funding, and that was comprised of 8,532 funding events. How did we collect this data? That's the part I'm going to talk about from now on. The problem to solve is not simple, but simple in a way that given the left part, given the article, news article about the funding, or maybe not about the funding, given the news article, curling them and find the funding articles and how can we transform that into the right one. So we want the data to be structured in a way that we have the numbers, we have the series, we have the list of investors, we want to have the date so that it can be used for search later. It can be used for the further prediction later. So here comes my spell number 2 is the slice and dice. So just given the fact that there is a big giant, this problem of let's find the funding information around the world, that sounds like a pretty big problem. That's like building the house. So just trying to applying the machine learning algorithm somehow directly into there doesn't really make that much sense because machine learning algorithms on its origin has like classification problem, clustering problem, reinforcement problem, that's all like smaller problems. So you need to slice and dice the problem into the smaller chunks so that the machine learning algorithm can be applied to this bigger problem. So this is how we chunk down the problem into the smaller problems. Firstly, given the funding, all the articles. So I'm not going to talk about how we build the crawler, how we build the pipeline of the data. I'm just going to talk about the machine learning part here. Given that we crawl the articles from the source, we first build the classification algorithm for say if this article is about funding or not. After that, let's say that given the funding article, we build a classifier that's only extracting the funding related sentences there. And then after that, from the sentence, we were able to extract the funding-related entities. And then finally, we build a confidence score, which is saying how likely this information that we extracted is correct or wrong. So the first part was to classify the funding article. So that's pretty simple machine learning algorithm. So given the news article, we used the TF-IDF-based feature extraction. Actually, we used a bunch of different algorithms, but we ended up using this. And then just the SVM classifier that says if it's the funding-related article or not. And that gives us pretty good precision. So suddenly there's another spell 3 here, so understand your domain. So while working on this, I realized that know more about the domain of the problem that I'm working on is actually helping me a lot on solving the problem. I'm saying this because after classifying the funding articles, we realized one interesting thing. Out of all the funding articles that's listed in there, so normal funding article is like comprised of like 50, 60 sentences. There are a lot of unnecessary information. There are information such thing as like this founder also built the other company on year 2012, which was successful, or someone even make the like joke like who ate the breakfast for what, or there are a lot of like unnecessary informations in there. So we just wanted to find the information that we wanted, and we realized that by taking a look at the funding articles, we were able to find the 3 different type of main patterns that are the information that we'd like to get. So by taking a look at the data, we were able to find the 3 different types of the funding sentences patterns. The one that looks like company blah, blah, blah has raised this much amount of money with the Series A funding. That's the amount and series type of the sentence. There are also other types of sentences that says this intercapital led around with the participant from the this company, this investors. That's the investor only. And also there's like the combination of both amount, series, investor. This company A has closed the 3.5 million Series A round led by this capital and that capital and blah, blah. So after we realized that, what we did was we decided to build a binary classifier for these 3 different types of the sentences. And this is the result. So here we used a little bit more complicated approach. So we built the 3 different classifiers using the word-to-back, which is previously trained from the word chunk to come up with the feature. And we did some semantic role labeling in there, and then we put it into the gradient boosting classifier. So as a result, given the article like left, we built a system that can find the sentences like right. The colored sentences are the one that we found out that is the funding related sentences. After that, the next step was much easier, because since we know that what kind of sentences are important in there and what are the types of sentences, we can just apply the regex parsing and named entity recognition in there. So for the investor-only sentences, we can just apply the named entity recognition and believe all of them are the investors. Or like for the amount-related sentences, we can just apply the regex parsing of finding the dollar amount and the number so that we can say that's the funding amount. So in the end, from the left article with color sentences, we were able to parsing out the right ones. So the spell number 4 is think probabilistically. So using the models that's probabilistic is helping people a lot, many times. What that means is, so we have these entities extracted from the funding articles. So what? Are we just putting into the database? Actually, no, because even though I said everything went well, like smoothly, there can be the room for error on every single corner. Like it's possible that it found the wrong sentences. It's possible that it found the person's name as an investor name, blah, blah, blah. So in the end, we build one other algorithm called confidence scoring. So given everything we extracted, everything we have done, make that as a feature, and we built another classifier. In this case, it's trying to classify if information extracted here is 100% correct or not. And then for that classifier, we pull out the 0 to 1 scale probability score so that we can know how likely is the information we extracted is correct.
Is this probability score the output from the gradient boosted classifier, or are you creating it?
So the question was if this 0 to 1 scale probability score was created from the previous gradient boosting tree classifier. Actually, we built the additional classifier on top of everything we extracted. So the gradient boosting tree classifier was being used for each type of the sentences. So there were like 3 different gradient boosting tree based classifier. And given that all information is in the database, we just added like additional step of the classifier.
So what were the inputs to this classifier?
So input to this classifier was something like how many sentences are there in the article, how many funding type of sentences in the article, how many investors did you find out, like what was the position of the sentences, because like normally, as you can see from this example, like normally the important sentences are coming in front of the article, so that where the position was at is a good indication that if we find out the right information or not. So that kind of, there are like numbers of the information, the features, but that, to name a few, they were some.
What are the data sources you get used?
Say again?
Data sources?
Oh, data sources. So the way how we find out the data sources is, so I'm saying as if like we were building it from first till the end, but that's like, this is the result of a lot of different iterations. So at the first, we were doing it like total manually. So when we were doing total manually, we found out going into the like something that's well known for having a lot of articles, like TechCrunch is one of them, like PE Hub is one of them. And we added like them gradually as data analysts find out the new sources. So yeah, there are like hundreds of like new sources there, and every time we add them, we are testing the system again. So it's basically any news article for now that's in English. All right, so confidence scoring is done. The reason why we did the confidence scoring is actually to come up with the last point. The last spell that I named it is the human plus machine. So let's get the help from mighty human being, not entirely rely on machine. What that means is that when I'm trying to solve this, when people are trying to solve the problem using machine learning, like getting into the 80%, getting to 90%, and getting to 99%, getting to 100%, there is a step function of how much resource and effort you need on each additional 1% gain. So for example, if I build a system that can achieve the 90% accuracy, going from there to 100% is like totally different story. Instead, if you just come up with the 90% solution and combine it with the human's manual approach, that actually ended up being working much better. So what we did was, since we built a confidence score, we built a web view version of all the articles we found out is about the funding. And for anything that has confidence score higher than like 0.9 or 0.8, we put them automatically to the system. For anything else that's between like certain confidence score, we are showing it to our data analysts so that they can decide what to do from there. So by this approach, we were able to get this much amount of the data with only 4 data analysts on year 2015. We still have only 4 data analysts.
Were you able to use the results from the data analysts and feed it back to your machine learning algorithm to make it better?
So the question was, were we able to use the feedback from data analysts and feed it back to the algorithm so that it can be better? The answer is yes. So originally, the way how it's trained was, the training data was coming from the data analyst. And as data analysts started like putting more information to here, of course we have more data and then we can feed it back. So yes, that's definitely the case. But we are in still middle of building this ecosystem of like feedback and like this output is feeding into this input, so it's still to be done more, of course. So that's how we solve this problem. So this is the summary slide. The 6 thing here. The firstly, machine learning is a powerful hammer. It's not like robot yet. Spell number 1 is know your enemy. There are a lot of trade-offs you need to make when solving something. You need to understand what problem you want to focus on to get rid of this bottleneck. Spell number 2 is the slice and dice. Given the chunky big problem, trying to dissect it into the smaller problems so that each problem can be either solved by machine learning or some other easier solution. Spell 3 is understand your domain. Know more about your domain will help you coming up with the better machine learning approach. Spell number 4 is probabilistic, like building the model in probabilistic way so that it can be, instead of like saying that this is correct or this is wrong, if you know that this is like 80% correct, then you can come up with the better way to manage it. Spell number 5 is human plus machine. So basically, machines are really dumb, humans are really clever. The only reason why we are using machine learning is machine is dumber, but they are cheaper. That's the reason why we are using machine learning. So by combining human and machine approach, you can get things done better in less resource. So we are hiring, we have 3 machine learning engineers at the team. We are hiring machine learning engineers, we are hiring data analysts, we are hiring everyone. So if you are interested, you can contact us. Also, my colleague who's sitting in front line here, Samir Rahman, is actually going to talk about more of our machine learning approach. So here we're talking about building the semantic search based on all the information we collected using this machine learning idea. So I believe he will talk about more about the actual machine learning techniques we use and the infrastructure we use. So if you are interested in, go to that talk at 4 p.m. Thanks for listening to my talk. These are the contact information you can reach to me, and any questions?
So is this approach applicable to pretty much all classified machine learning?
The question was, is this approach available to be used for the all classification problems? The answer is maybe. So the reason why I named it like black magic, not magic, is because a lot of the things in the machine learning, even the algorithm itself is like deterministic. The way how people are using it is really undeterministic. So for example, I show you the 3 phases of our machine learning engineers. For any given problem, the way how we are solving the problem is totally different. I used to be the fan of support vector machine. Samir Rahman was the fan of the gradient boosting tree. I like to use less features. Someone likes to use more features. Someone likes to do the cross validation. Someone likes to do things manually. So the spells that I came up here is the lessons that I learned while working on the problem. So a lot of them can be useful, but I'm not going to say these are the theorem or axiom on building this stuff.
For the smaller company that you actually mentioned, you did quote the number of, for me, your sample set is small. That's why it's not necessarily statistically sufficient sample set compared with a large one. That's why if you have outlier and so on, you will impact more your result. So actually it's very different from dealing with a domain that actually have sufficient sample. It's more statistical or stochastical. And then you can endure more variation, still being accurate. And that probably is the power we want to do, because it's harder to analyze a large scale data with machine learning. Probably with the right approach, you probably can solve them more automatically. Do you agree?
So his question was, how would I put it?
I think you are biased to a smaller sample set, and it's not statistically sufficient.
Yep.
And that's why your approach is slightly different.
So what he said is that since we are working on the smaller data set, there's a possibility that there's a bias in the data set and statistically, and that's why we are trying to do the things in different way than when we have a lot of data. That's exactly 100% correct. So the trend in machine learning for the big companies is that collecting more data, put them all into the GPU-powered machine with the deep learning, let the neural network take care of everything. As you build more and more and more machine power, it will get better. That's actually kind of trend where things are going. The things that I talked about here is mainly more about like how can we fight the battle when we don't have enough data? Because any startups in the world that when they are created, they will have not that much data. So from there and going to the like bigger data part, so there of course will be the bias in the data in a statistical sense. Then how can we fight that bias? How can we prevent it from overfitting? All these things can be done by using some sort of different techniques than when we have larger data. And I think some of the things that I mentioned today is about that. So
in the information theory, there's a way to say, given a sample set, if you have this dimension, and then whether you have sufficient sample set to begin with.
yes,
I think that's very important to say, how should I solve this problem?
yes. So what he said is that in information theory, there is a theory that you can say how much data is sufficient for you to say this is sufficient amount of the data to make the decision. And yeah, that's what he said. So
Could I ask how many data entry you have per company?
how many data entries I have
Shouldn't be
per the
many.
company? I don't think I can answer that question. Thank you. Any other question? Yeah.
Yeah, so in one of the slides, I think in the initial part of your machine learning, you showed like something plus SVM plus prior. You also mentioned you tried a bunch of others and SVM was probably the best. So I guess my question is, for most of the problems I've done, I've found SVM and logistic regression kind of perform similar, or maybe SVM is a little better. But I still go with logistic regression because it's easier to explain. It's also easier to transport it to other people, or easier to scale. So do you have any thoughts on that?
So her question was, in most of the problems that she were dealing with, she used the SVM or logistic regression, and they both show the similar performance. But she anyway went with the logistic regression because that's easier for her to explain it to the people who are not machine learning person. So the question was what kind of thought I have about that, right?
Yeah, like did you go for SVM because, like why did you go for SVM, I guess?
The simple answer is it worked better in this case.
Okay.
It worked better compared to the logistic regression and all other approaches. So for here, as I mentioned, like getting the better accuracy was really important. So the explainability versus like accuracy, that's the.
But our scalability was also not a problem, I guess.
Scalability was also not a problem because like as you already know, logistic regression is really easy to scale compared to the other algorithms. So yeah, that's probably the reason why we did choose that. Any other question? Yeah, so this is going to be the last question.
So as scale increases, will your model change over a period of time? Like today, SVM may sound fantastic for this problem, but if your data increases, probably some other model may be a better fit. So how will you manage that change?
So the question was, as data increases, for now, SVM or Gaussian boosting tree was working best, but like as data increases, some other approach may work better. And how do we deal with that change? How we plan to deal with that change? That was the question. So our plan is we are planning to building the whole pipeline of like doing the retraining and compare the retrained model to the previous model in a way that if that makes sense to making the change to the retrained model. Because so we are only scratching the surface of a lot of different things, and we are actually in middle of building the ecosystem between this classifier, that classifier, and that classifier. So as we change the one part of it, the other part will be affected. So we are planning to building the system that's given the new motor compared to old motor, and if it's working better, switch it. If not, leave the existing motor kind of thing. So that building that kind of system is our scheduled solution for that. Okay, I think that's it for my talk today. Thank you very much.